Our next presentation is Understanding Power Efficiencies in Electrical Heating and How to Save on Energy Costs. A clean energy revolution is taking place across America. IGBTs reduce the congestion in power delivery, which results in a smooth electrical delivery and reduces energy costs. This presentation takes a deep dive into understanding the power inefficiencies and solutions in a typical vacuum furnace used for heat treatment. Please welcome our next speaker, David Pridmore.
Good morning. My name is Dave Pridmore, and I'm presenting Understanding Power Inefficiencies in Electrical Heating, How to Save on Energy Cost. So I'm a sales application engineer for Roman Manufacturing. My work focuses on the commercialization of new products, as well as electrical sizing and integration of systems. I have a Bachelor of Science in Chemistry, and I have spent most of my career in a lab environment. I now apply my experience with the scientific method to new products and technology. And Roman Manufacturing, the company I work for, is located in Grand Rapids, Michigan. Roman Manufacturing's vision is to become the global brand of choice for industrial power conversion solutions. So before we get into the technology, I want to first comment on the current state of industrial electricity. Industrial electricity is getting more expensive. The Bloomberg article shown here describes how 600 workers at the second largest aluminum mill in America lost their jobs because the plant couldn't afford the electrical bill. Summer 2022 is projected to set the highest electrical rates on record. These increased electrical rates are hoped to be curbed by a recently passed Inflation Reduction Bill, which in part aims to incentivize clean energy technology. So the evidence is clear. Heat treaters can no longer ignore or overlook electrical inefficiencies in their systems. The more important point, however, is that all heat treaters have access to these incentives and rebates if they clean up their energy use. So now, taking a deep dive into the electrical portion of the talk, here's a summary of the variables at play in a typical electric heating system. Starting on the left side, you have a typical service line, and this is where power is billed. Electrical billing is made up of some combination of kW, kVA, power factor, and peak demand. I have shown on this slide here an ammeter and voltmeter. So kW, or kW hours, is typically billed directly, where kVA can be billed directly or indirectly through power factor penalties or peak demand charges. The ammeter kind of describes how kVA is a better way to understand power, because kVA is actually what determines the amperage and current going through your system. And this is what you get billed for peak demand charges, as well as circuit breaker sizing in a system. So the first part of a power control system is the power controller. Historically, there's ignitron tubes or thyristors. These are just rectifiers that control power to an application. These were used prominently in the 1930s and 40s. And then came the VRT, or variable reactance transformer. A variable reactance transformer is actually a power controller and transformer in one. There's a DC saturating coil that saturates or desaturates the core of a transformer to control power to an application. And then we have the common day SCR and IGBT control types. SCR stands for silicon controlled rectifier, and IGBT stands for insulated gate bipolar transistor. The power controller then puts power into the load, or actually first into a transformer. In this industry, the typical transformers you will find are air-cooled or water-cooled transformers. With an IGBT control type, the type of transformer used is called an MFDC transformer, or mid-frequency direct current. And we'll go into what exactly that means later. The power is then delivered to the load. I have shown on here water-cooled cables, but typically the best way to understand the heating circuit is that anything after the transformer is essentially the heating element. This can be accomplished through water-cooled cables, the high current transfer, or large copper cross-sections. I have shown on here Joule's law, which is heat is proportional to I squared RT. This shows how the current is directly proportional to the heat output. And this we'll get into later as one of the components that we can optimize in a system to improve electrical efficiency. The power is then delivered to the load. In this industry, you can typically see molybdenum, graphite, or silicon carbide heating elements. Another important variable at play in the load is also the type of current. Is it alternating current or direct current? And the actual physical size of the electrical circuit. And then finally, the most important variable at play is probably the operation or the time that in which you spend the furnace at certain set points. So, for example, when you have a furnace run, do you run at 100% full power the entire run, or do you ramp up to a temperature and then drop your electrical requirements to a plateau? This has a huge impact on the power quality and quantity that you find at the upstream service line. So in summary, these are the electrical components and variables at play in a typical heating circuit. This is kind of the standard model that we'll look at through multiple scenarios to understand where you're losing electricity or there's electrical inefficiencies in the system. So here is the first example of an electrically underperforming furnace. This case demonstrates why operation of a VRT at low power set points is electrically inefficient. This furnace is powered with a VRT rated at 375 kVA, which equates to 125 kVA per zone at 46 volts and 2,700 amps. So this cycle is also shown on the screen in blue. This cycle consisted of a ramp up to and hold at 1800 degrees Fahrenheit. So on the surface, everything appeared fine. This run was completed without any issues. On the surface, everything looks fine. That is until we examine the electrical characteristics of the furnace. The graph below shows the total power consumption of the furnace, shown in blue and red. The red area represents kVA, which is the total power, and the blue area represents kW, which is the power that's doing work in an application. The reference on the right here is the beer mug analogy for the power triangle. And basically what this describes is kW, the real work that's going on in an application is the beer, and then the foam, the reactive power that's not doing any work is the foam on top, which no one wants. The electrical trend here is what we expect to see in a furnace. So as the furnace is ramping up in temperature, it takes more energy at higher rates. And then when the furnace reaches a soak phase, the energy requirement drops down to a plateau. That's actually very bad for energy quantity and quality. The best way to understand this is to look at the total kW hours versus the kVA hours. For this run, the total kWh hours was 140, and the total kVA hours was 299. That means that only 43% of power to this application is actually doing work. That's about 60% foam on top of the beer. Another important note to make on this graph is the rated capacity of the furnace. This was rated at 375 kVA. At the maximum point in this run was, in terms of kW, was 120 kW. So in other words, this furnace was operating at 26% of its maximum rated electrical capacity. And these inefficiencies that occur because of that really impact the bottom line. So if we go back to the standard model that we described earlier, more kVA demand is billed, either directly through kVA billing or indirectly through power factor charges or peak demand charges. How much? An impressive way to describe this case is with peak demand. With a VRT system in place, the peak demand was 250 amps. However, with that kVA inefficiency addressed, the peak demand was reduced to 125 amps or 50% less. This introduces the comparison between a VRT power supply and an IGBT MFDC power supply. With the VRT power supply, going back to the beer mug analogy, the beer mug is fixed in size, and so the less beer you put into it, the more foam you get. But with an IGBT MFDC power supply, the mug grows and shrinks with the cycle, always giving you mostly beer and little foam. Now, to take a short aside on sizing, you may ask yourself, well, why didn't we size this furnace at 26%? The issue is that conflicts with the use case for this user. Heat treaters want to be able to use their furnace at any set point without having to limit it and still have the efficiency there. If you look at the graph on the right, you have the VRT in blue, and then now with an IGBT MFDC system in red. And you see that the IGBT MFDC system total power is very close to real power in this application. So in summary, VRTs place a disproportionate electrical burden on the power grid, and IGBTs are an adaptable alternative that optimizes use for each use case. So before we move on to case 2, I want to discuss briefly the difference between kVA and kW savings. We went over the power triangle briefly in the very beginning, and this is the beer mug analogy. So on the x-axis, you have kW. That's the real power, the power that's doing work in a process. And then you have on the Y vertical axis, kVAR, which is the reactive power that's not doing work. The action shown here in the triangle is what we discussed in case 1. When you have a reduction in kVAR with the same kW, you have a reduction in the overall kVA. So what about kW savings? This introduces the impedance triangle on the right. I have the axis as shown on here as real and imaginary, but it's a similar triangle where you have real and reactive components that are 90 degrees out of phase. However, the vectorial sum now is impedance measured in ohms. Simply put, a reduction in impedance in the system is a reduction in the total kW hours that's used for that system. This is demonstrated with a simple circuit shown on the lower right. You have a simple circuit with a resistor that has impedance Z with current I passing through it. The equation shows that power is proportional to impedance Z through the system. So you can see that as you reduce impedance, you can reduce kW. So how do we eliminate excessive resistance and reactance? Going back to the comparison with the VRT power supply, an IGBT MFDC system reduces impedance through not masking, but total elimination of reactance with direct current. And it reduces resistance through shrinking the transformer, reducing the secondary high current portion of the circuit, and moving the power supply closer to the hot zone through what we call close coupling, and I'll show you some pictures of that later. So here's another way to look at the impedance triangle, but through the lens of that standard model that we were discussing earlier. So in a circuit, this is a standard circuit with a transformer load, and you can see that you have resistance and reactance in the primary circuit, resistance and reactance in the secondary circuit, and resistance and reactance in the load. The important note here is that the only component of power that's doing work is resistance in the load. The rest of the components of power, they do no useful work in a system, and every effort should be made to reduce them. I mentioned in the last slide that reductions in reactance is accomplished through direct current. So the equation here shows that reactance at the bottom, X sub L is equal to 2 pi FL. So this shows that reactance is proportional to the frequency of the waveform as well as the physical area of the circuit. With direct current, there is no frequency, and the reactance is completely eliminated. So this leads us into our second example of a electrically underperforming furnace. Specifically in this case, we'll look at the effect of long water-cooled cables in a system. This is a 5-zone system rated at 615 kVA. This consists of 3 side zones at 150 kVA, 1 top zone at 55 kVA, and 1 bottom zone at 110 kVA. The cycle was run, which is shown here, and it consisted of a ramp up to and hold at 2200 degrees Fahrenheit. The water-cooled cables in this case consisted of 4 14-foot cables, 4 18-foot cables, and 2 20-foot cables. In the picture here, you can see the water-cooled cables draped over the catwalk between the VRT power supply and the furnace chamber. So the power loss in the cables was then measured across multiple furnace set points. The power loss was calculated by taking measuring the amperage across the water-cooled cable as well as the voltage drop across the cable. That was then used, the product of that was used to calculate the power drop. The graph on the left shows the power drop by percent power. So the purple line at the top, for example, shows that at 80% power, this cable is continually dumping about 5.5 kW into the water, whereas at 40% power, it's 4 kW. Remember that water-cooled cables are just a resistor wrapped in water. And so this introduces the value proposition of reducing that high current circuit outside of the hot zone to improve electrical efficiency within a system. So how does an IGBT MFDC power supply work? Here's a pictorial schematic of the process. And if we start on the left side, the input into the system is 480 volts at 60 hertz, 3-phase. Other main voltages can be used. We just show 480 volts here. Within the IGBT control, SCRs then rectify the 3-phase up front to a 650 volt DC bus. It's smoothed with a capacitor and then delivered to IGBTs, insulated gate bipolar transistors, which turn on and off the waveform at 1,000 hertz. You may ask, well, why did we use 1,000 hertz versus 60 hertz? A good analogy here is the transformers they use in planes. They don't use 60 hertz transformers, use 400 hertz transformers in planes because that higher frequency allows you to shrink electrical circuits. And this also allows us to shrink our transformer considerably, and then allows us to take that transformer and apply it directly to the power feed-throughs on the furnace. We actually have a power supply at our booth as well, so you can come visit us there to see how much smaller it is. It's a 200 kVA transformer that's about the size of a bread box. The 1000 hertz, 650 volts is then delivered to an MFDC transformer. That steps the low current, high voltage power down to high current, low voltage power. Within the MFDC transformer, there are then diodes that rectify that 1000 hertz AC waveform into low voltage, high current DC power. That DC power is then delivered to the load. At the bottom of the screen, you can see kind of the inner workings of an MFDC transformer, which shows how the rectifier is very closely coupled to the transformer. It's that high current circuit between the transformer and the rectifier that's extraordinarily inefficient. It's also important to note that the losses in a system are proportional to the magnitude of current change. So in a secondary circuit where you have that high current power, which you need for heating, that high current power is also very inefficient. And so you want to make sure that that high current power is just used for heating and not for anything else. So another key portion of this system's value proposition is this high voltage power transmission. If you think back to the early days of Tesla versus Edison, they had a big competition between AC and DC, and AC ended up winning out because they were able to transform the voltage to a high voltage, low current, transmit the power, and then transform it back into high current, low voltage power. We're using that same concept here, where we're splitting up the power supply. Instead of having a VRT that's 30 feet away from your power feed-throughs, we're using high voltage power transmission to bring that power directly to the power feed-throughs, and that makes the system incredibly more efficient. A summary of the advantages can be seen here for an IGBT MFDC control. Some of them include it utilizes all three phases of power and balances the three phases. The higher transformer turns ratio from that higher voltage allows a lower peak current demand through the system. Another point is that if you have any inductive loads, that DC completely eliminates the inductance in that load, whereas with typical SCR, VRT, any type of control type, you're not removing that inefficiency, you're just masking it with either capacitance banks or power correction in your facility. With an IGBT MFDC system, that inefficiency is just not there in the first place. Again, the smaller transformers with the increased frequency allow the infrastructure to be smaller and to move those power supplies closer to your power feed-throughs. Some of the downsides to an IGBT MFDC system include 3 phases upstream is required. The IGBT MFDC system is only able to produce single-phase power output, so we can't do 3-phase heating elements. Water cooling is required. And the component of the power transformations through the system sometimes have a higher total loss in some applications, and it wouldn't be useful in those applications. So I have some other slides at the end, but in conclusion, here's a summary for our talk. We have evaluated the typical electrical characteristics in the furnace. We have discussed the limitations in the predominant power supply technology, and we have presented solutions offered by IGBT control types. So now I'm going to get into some of the pictures that I put on the end here. I was trying to move those around earlier. So here is a good example of close coupling where we have the MFDC transformers directly mounted on the power feed-throughs. And this is as opposed to having like a VRT power supply that's farther away from the system. So with that, thank you very much for joining me today. Do you guys have any questions? Yes? I don't think I should comment on that, but we have several OEMs and end users that we're working with right now. But if you visit our booth, we can discuss more about that. Other question?
If you go back to that last slide, if you tell us what sort of power those transformers up on top of the furnace are, if I make an example.
Oh, yeah. So for that application, I have to do some quick math here. So for this application, there's 5 zones. The 3 inner zones are 248 kVA, and then the outside zones are 86 kVA. Another question?
In the schematic that you showed, mentioned that SCRs and IGBTs were used, sort of like the initial replication inverting stages. I believe you said SCRs there, and then IGBTs later. Why, it's my understanding that certain powers are interchangeable, so why the selection of one, why not IGBTs throughout?
So IGBTs are more expensive, and they're better used for the high frequency transmission of power versus the rectification. They're not able to turn on and produce that square wave as fast. So the SCRs are just used at the beginning of the component to rectify to that DC bus. We have actually looked at using MOSFETs for the secondary circuit, but SCRs just don't have the capacity to do what the IGBTs are able to do.
It's also my understanding, in practice, maybe it's theory versus practice, IGBTs are typically, in the right application, reliable. Has that been your experience?
So yes, overall, and it really doesn't have to do with the component of an IGBT itself. It has to do with the control that's built around it. So, this control is constantly monitoring the power output on a microsecond basis, and that's what really gives the robustness to the system. It's not the component itself; it's like a field programmable gate array that's constantly assessing the system, and that's what contributes to its robustness. The other aspect of a IGBT control type is, the analog digital feedback that you can get from it. So, it can be constantly monitoring the load. It can look at resistance in the load and monitor how that changes. But it's really the brains behind it that offer that robustness. Like if you have, these are water-cooled components as well, but it's also monitoring that chill plate temperature so that if your water goes out, let's say, it will shut down the system. But so that's kind of, the robustness comes from not the components, but from the control itself. Any other questions? Well, thank you very much. Appreciate it.